Hello, everybody. Welcome to this week's 1W-MINDS seminar. I am very happy that Nick Dexter from Florida State University has agreed to show up this week and tell us about his expert knowledge on the topic of sparse approximation techniques for parametric PDE. So I'm looking forward to the talk, and I'll turn it over to you, Nick.
Thanks, Mark. And thank you for the invitation to speak here. So this is a follow-up on some of my recent work with Ben and Simone and Ben's former PhD student, Sebastian. And this is work with also my PhD student, Kunal, here at FSU. And so I'm going to give you an overview of what we're trying to do here. Which is looking at specifically applying L1 minimization-based methods for sparse approximation of parametric PDEs and these kind of operator learning kind of problems. To do so, let me first introduce PDE operators arising in computational science and engineering and UQ. So consider these PDE operators mapping function spaces to function spaces, i.e. of the form x in script x or calligraphic x here to f of x in y, where x here is the PDE data, i.e. The initial or boundary conditions, forcing functions or parameters, and calligraphic x is the data space. Capital F here is the operator we're trying to learn, and then y is the PDE solution space. So of course this depends on each PDE that you solve. X and y here could be Hilbert spaces or Banach spaces, but they're generally infinite dimensional function spaces. And in operator learning, the goal is to capture the dynamics of the PDE operator F using surrogate models, typically based on deep neural networks or polynomials trained on data. So here we're going to let mu be a probability measure on X, and we're going to consider noisy training data given by these pairs xi and f of xi plus ei. We'll have m of these examples that we're going to use for training, and we're assuming that these xi's are drawn IID from mu, and that ei is some noise term. So I'm going to need some notation. So first, let me define the Bachner norm. So if I have x and y are Banach spaces and mu is a probability measure on x, then the Bachner LP norm of a strongly measurable operator f from x to y is defined as the LP mu of xy norm of f, which is the integral over x of f of x's y norm to the pth power with respect to the measure mu, all taken to 1 over pth power. And for p between 1 and infinity, this is how we define this, but for p equals infinity, we define it as the essential supremum of over x in calligraphic x of f of x's y norm. And we'll also need this idea of these LP lambda y weighted spaces. So for p between 0 and 2, and a multi-index set lambda, and a weight sequence W, the weighted LPW space with lambda and y is the space of sequences V for which the PWY norm, which is defined as the 1 over pth power of the sum over nu and lambda of W nu to the 2 minus p times the y norms of V nu to the power p is finite. And we write the p vector. So typical example that might arise, and apologies, I'm already seeing it now. Your internet is unstable notification. If this becomes a problem, just let me know and I'll switch to my phone tethering. Unfortunately, Wi-Fi is a little bit of an issue in this room. So the typical example of Hilbert valued parametric PDE problems in UQ, you have some input X, you have a black box model, and you have some output F of X and Y. And then you use that to compute some quantity of interest. So some other function Q is applied to F, and that's what you're really interested in. The typical Hilbert valued example is you take a parametric elliptic PDE problem. and you introduce this parameter vector y. So a of xy is this is a random field. You might consider, for example, the KL expansion of the random field. This leads, of course, then to a family of PDE problems depending on a and x, or the parameter vector y and u. In other words, this results in an operator learning problem involving the map f taking a and x to u of a and y. Or equivalently, and we will see later, the operator f taking y and u to u of a of y in y. This is the actual version we'll focus on in this talk, the parameterized version of the operator learning problem. Okay, so I need some assumptions. The first is I'm going to assume that I have a certain kind of smoothness called holomorphy in my parametric dependence. So first I'll define a Bernstein ellipse. This is this E rho. So given rho greater than 1, we define E rho as the set vectors z, or of complex numbers z plus z inverse over 2, such that z is in C and its magnitude is between 1 and rho. And then we can define the polyellipse by taking the tensor product of these. And this illustration on the right here shows you how these look in the case of the simple Bernstein ellipse. And we're going to define what it means for our function to be holomorphic. So let epsilon be greater than 0, b in L1 with b greater than or equal to 0. We say a Banach valued function f from u to y is b epsilon holomorphic if it's holomorphic in this region r b epsilon, which is this union of these Bernstein polyellipses with rho greater than or equal to 1. And rho here is, of course, vector, so we're considering this component-wise. Then we have the sum from j equals 1 to infinity of rho j plus rho j inverse over 2 minus 1 times these bj's, less than or equal to some epsilon. And here, a large value of bj means that f is less smooth, and smaller values of bj means larger polyellipses and functions more smooth. So rescaling b, we can always assume here that epsilon is 1, and for convenience, we're going to define this space or this set HB here, the set of mappings f from u to y that are b1 holomorphic, and they have y norm bounded by 1 for all y and rb1. Okay, so the standard approach, or at least in the past, has been to use polynomial approximation, and so we're going to use the following setup. We have u as the unit hypercube. Rho is a tensor product probability measure on U, and we have an orthonormal polynomial basis, L2 rho, which is formed by taking these psi nus and taking the psi nu k's, the one-dimensional basis functions, taking the product for some multi-indices. And some examples include the uniform distribution, which leads to the Legendre polynomials, and the Chebyshev distribution, which leads to Chebyshev polynomials. We can talk about polynomial expansion of f. So this would be involving finding these coefficients c nu, which are the inner product of f against the basis functions. And these live in the space y. You might ask why would you use orthonormal polynomials? Well, we know that the smoothness in f implies compressibility of these coefficients c nu. So if you have an orthonormal Legendre basis, then the coefficients can be bounded by this beta the nu divided by nu factorial times the L infinity norms of the partial derivatives of the function f for some beta greater than 0. The first step is to now truncate this approximation in a basis selected a priori, indexed by lambda. And again, these c are the things that I have to compute. N is the cardinality of lambda, and some common isotropic choices here include the tensor product, total degree, hyperbolic cross, the Smolyak set. The algorithm costs here scale poorly with the dimensions, so n grows quickly with d, implying that I have to compute more and more coefficients with increasing dimension in order to gain the same, like say, total degree accuracy. The choice of lambda here also induces a truncation error. So if I look at f minus f lambda by Parsel's identity, this is the 2y norm that I defined earlier of the neglected coefficients from the set lambda. And the optimal choice here, lambda s, which is unknown in general, is to choose the s most effective indices to minimize the truncation error. Now this enters where we begin talking about compressed sensing. So the goal of compressed sensing is to find a sparse solution X of the underdetermined linear system AX equals B, where A is the measurement matrix and B is the data. And the key point here is that the locations of the non-zero entries are unknown. Of course, it says origins, going back to early work by Candes, Romberg, and Tao in 2006, and Donahoe in 2006. But since then, it's been the subject of thousands of papers, dozens of survey articles, and several books. It also caused an important philosophical shift, how we view reconstruction and inference tasks and applications like medical imaging, seismology, and others. And one way that you might approach this problem is to try to solve the underdetermined system via L1 minimization, i.e. Basis pursuit. You might ask why L1 minimization? We want to promote sparsity. Isn't sparsity measured by the zero norm? Well, there's difficulties with working with L0 minimization. First, it's not a norm and it's not convex. This set of all S sparse vectors, here I've got a picture of this in 3 dimensions. This sparsity 2, it can clearly be seen to be not a convex set. And unfortunately, you can show actually L0 minimization is NP hard. And so the key idea is relaxing to the L1 norm and searching in a large ambient space for a sparse solution. So the rationale here is that the smallest L1 norm ball intersects the feasible set. That's the set of vectors that satisfy AZ equals B on the axes. And you can see this in the picture on the right. Here I've got the minimization problem with the 2 norm subject to the constraint AZ equals Y versus the 1 norm with the same constraint. And the blue dot where it intersects lies on the axes. That means that the solution that I find from this minimization problem will be a 1 sparse vector. Whereas the solution from the 2 norm minimization problem is going to be a 2 sparse vector. So in a considered setting, this system is highly underdetermined. So how can we guarantee exact recovery of these vectors via basis pursuit? This is implied by the following. So this restricted isometry property of the matrix A, we say A satisfies the RIP of order S if there exists a delta in 0 to 1 such that 1 minus delta times Z's 2 norm squared is less than or equal to AZ's 2 norm squared less than or equal to 1 plus delta's 2 norm squared for all Z in that set sigma sub S n I mentioned earlier. And the smallest delta that holds such that this holds is delta S. It's called the restricted isometry constant. We know that many random matrices satisfy the RIP of order S with high probability, provided that M is scaling like some constants times S polylogarithmic terms in N. And then, for example, we know subsampled isometries like the subsampled Fourier transform or random Gaussian matrices also satisfy this. When we work with a bounded orthonormal system, like we're doing with the case of polynomials in the Legendre system, we can define this constant theta. And if our system satisfies that the essential supremum over y and u of psi j of y is less than or equal to theta, then this is what's called a bounded orthonormal system. And with A defined as 1 over root m times the matrix formed with psi j evaluated at yi at each I and j, with y1 through ym drawn from row iid, we have the following. So this is the RIP for bounded orthonormal systems. You can find this in Ben, Simone, and Clayton's book from 2022. It says let lambda be a subset of n0d and have cardinality n and epsilon between 0 and 1. And then with A as above and S in the set 1 to n, suppose that m is greater than some constant c0 times theta squared s times L. C0 is a positive universal constant, and L is this product of log 2 theta squared s times log 2 theta squared s log 2n plus log 1 over epsilon. So it's some polylogarithmic terms in theta squared s and n and 1 over epsilon. Then with probability at least 1 minus epsilon, A will satisfy the RAP with order S with constant delta S less than or equal to delta. What we were able to show in 2019 in some work during my PhD thesis is that We can reformulate this RIP problem to a certain version we called the YRIP or VRIP in the earlier papers, when we're considering a Hilbert space Y. And that says that there exists a constant, delta ys small, such that for all s sparse vectors z and y to the n, we have 1 minus this constant times, again, the same kind of inequality that we see in the RIP, but just with these two y norms instead. And this proposition, again, from 2019, with my work with Huang Tran and Clayton Webster when I was at Oak Ridge, says that A satisfies the RIP if and only if it satisfies this y version of the RIP. In other words, suppose Y is a separable Hilbert space, then, and that the matrix A satisfies this RIP with restricted constant, isometry constant delta S, then it also satisfies the YRIP with the same constant. This implies then the same sample complexity for this L1V minimization problem, which I'm about to define. And of course, a standard basis pursuit requires exact measurements. Lasso and quadratically constrained basis pursuit require noise level estimates to solve. Smooth functions also have a lot of structure in their coefficients. So weighted L1 minimization with the so-called intrinsic weights, these W nu set to the L infinity norms of the basis functions, this can capture this structure more efficiently. There's a lot I could say about this, but for the purpose of the talk, I'll just say you can see some of this stuff and easily covered very well in the book that I mentioned in the previous slide. So consider instead now the weighted square root lasso problem, or SR lasso problems. We want to minimize over Z and YN, lambda times the 1WY norm of Z plus AZ minus B in the 2Y norm. And we know that this, thanks to some work by Simone and Ben and Anyi Bao, is a noise blind problem. So it doesn't need lambda set proportional to the noise level in order to solve this problem. In fact, what we find is oftentimes you just set lambda to some small value and generally it works really well. So this is going to be what we focus on for the sparse approximation with polynomials going forward. And the problem setup is we have this square root lasso problem weighted with the intrinsic weights, which again, I mentioned promote smooth function recovery. Then we have our normalized measurement matrix and normalized measurement vector B, consisting of these measurements at the points yi. Then we can derive a primal dual iteration for solving this problem. So given some initial x0 and c0, we can define a sequence of iterates zn and xcn by, and this should be a z, I think. I'm sorry for the typo here. The zn plus 1 is the proxima map with tau g of zn minus tau a star cn, and then cn plus 1 is the proxima map with sigma h star of cn plus sigma a times 2 zn plus 1 minus zn, where the proximal maps are defined in the standard way. And furthermore, we can also apply a restarting procedure, which depends on a parameter zeta prime, and this will lead to exponential convergence, as you'll see in the next slide of the algorithm. And by the way, you can also see more about this in these papers here by Colebrook, Anton, and Hansen, and Adcock, Colebrook, and Neyra Nesterenko from 2023. Okay, so quickly I'll go through this. The next two theorems talk about how does it look when we try to solve this problem in the finite and infinite dimensional settings. What we were able to show is we get exponential rates of convergence in finite dimensions. So under our holomorphy assumption, assuming D is finite and M is greater than or equal to 3 and K is greater than or equal to 1, then for all T greater than or equal to 1 and zeta less than or equal to zeta prime, this restarted primal dual algorithm computes an approximation f hat from M samples satisfying this bound in the Bachner norm, zeta plus zeta prime plus e to the minus t for any gamma between 0 and d plus 1 inverse times d factorial, the product of the rho j's. The rho j's coming from earlier assumption about the holomorphy of the problem, all to the power 1 over d. And where zeta here is the approximation error, the sampling error, and the discretization error. And these are given here. You can see the approximation error is decaying exponentially quickly in M. There's also this 1 over d factor showing that the convergence is impacted by the dimension as well. The sampling error, this is empirical average of the noise that we have, and our discretization error. This comes from the fact that we're working in YH, some discretized finite element space, instead of the infinite dimensional Hilbert or Banach space Y. We're also able to derive that the cost is algebraic in M for fixed dimension here. You can see the cost estimate here. We also, like I said, we're able to show this in the infinite dimensional setting. So under the same holomorphy assumption, then the restarted primal dual algorithm computes an approximation with the same looking error bound. But now instead, the approximation error is decaying algebraically fast instead of exponentially fast in M with this rate. But the cost is also algebraic in M. Next, I'll show you some numerical examples where we applied this to simple parametric elliptic diffusion problem. So here, this is using compressed sensing with Legendre polynomials and a hyperbolic cross multi-index set, which again is another choice that helps to promote smooth function recovery. N was chosen to be 184, which leads to a cardinality of about 1,000 for our basis. And then our model PDEs, again, parametric diffusion problem with this test function down here for the diffusion coefficient, a simple 2D example. And on the left, you can see the ergodic sequence relative L2 error with respect to the number of iterations. And then on the right, you can see the error with respect to the number of samples. So I think we fixed here 20 or so samples and then ran this problem multiple times. That's where you see the envelope for the standard deviation. And on the left here, we were verifying that this choice, you notice in both of these statements, we say zeta has to be less than or equal to zeta prime. And zeta prime is something that shows up in the algorithm. So we're verifying here that zeta prime can be set arbitrarily small, and you still get a good convergence that matches what the theory predicts. This is a 2D example, and it looks nice. When we go to a higher dimensional example with a more complicated coefficient, obviously things are going to change. It is a 30-dimensional example now, and N is set to only 10 as opposed to 184 in the previous, and cardinality here is about 7,800. But now we have this more complicated log transformed diffusion problem with this corresponding to the squared exponential covariance kernel. And due to the decay here, we're seeing a lot slower decay in the coefficients of the solution, and therefore much more difficult time approximating the solution of this PDE using the sparse recovery approach. But we still see largely good agreement with the expected convergence of the algorithm. And we get down to about 10 to the minus 2 error with about 1,000 samples. Some takeaways. So far we observe exponential rates of convergence in M in finite dimensions and algebraic rates in infinite dimensions. The error decreases here with zeta prime, confirming that this dependence on zeta prime is an artifact of the proof. The computational cost is algebraic in M, confirming our theory, and solving and evaluation are very fast with this setup, especially with new work by my student Kunal on GPU accelerated versions of the algorithm. There is one caveat to that, though, is that, and I'll mention this at the end of the talk as well, it does involve some rather costly computations of the norms, of the components, of the vectors, of the iterates of the algorithm that you're working with it. And so far, we've not been able to offload that to the GPU or find a more efficient representation. So we're just relying on the built-in norm function in Phoenix, which is what we're using to solve. Okay, so I'd like to also compare against some recent work we've had on neural networks for the operator learning problem, where we consider these approximate encoders and approximate decoders, and then a neural network n hat, which approximate the operator through these compositions. And these are either specified by the problem, these encoder and decoder, or they're learned separately from the data or concurrently with n hat. But the goal, as in all of these supervised learning problems, is to ensure good generalization via the learned operator f hat from as little training data as possible. As before, we're focusing on learning classes of holomorphic operators with arbitrary approximate encoders and decoders. We're using standard architectures, feed-forward DNNs. I'm sure you've all seen this many times. You have a component-wise activation function, and you have affine maps, and then you compose alternating affine maps with activation functions to construct the network. We use the same kind of standard definitions for the width and depth of the network. And then we denote a class of these with a fixed architecture, i.e. fixed activation depths and widths as a calligraphic n, and we write the same width of n and depth of n are the same. Some further notation. So given a measurable mapping iota and a measure mu, we define the push forward of mu as the measure I sharp mu given by I sharp mu of b is mu of iota inverse of b for a measurable b. I'm also going to define the LP space, standard LP space with the quasi-norm, and the minimal monotone majorants z tilde of the sequence z as z tilde i's, where z tilde i's are the supremum over j greater than or equal to I of absolute value of zj. And the monotone LP space, then LPM is the space of all z whose minimal monotone majorant z tilde is an LP. These assumptions are somewhat heavy, but I assure you, as you'll see in the next slide, they're kind of standard. But let's say we're working again in the setting of -1 to 1 now to the n, and rho is a uniform probability measure on u, and we have f as an operator we're learning. Then we have e tilde taking x to r dx, and d tilde x taking r dx to x, and then ey taking y to r dy, and dy taking r dy down to y. These are approximate encoders and decoders for x and y respectively. We have these four assumptions. One is that there's a measurable mapping iota such that the push forward measure is quasi-uniform. Measure supported on u and it restricted to the support of mu. The measure iota is Lipschitz with constant L iota. The second one is that the operator f has this form f composed with iota, where f is an HB for some b in the monotone LP space, and p between 0 and 1. And then the third one says that we have e sub x, which is component or the composition of iota dx, d tilde x, and e tilde x is a measurable mapping, where iota dx is the restriction of iota to the restriction of iota dx, and the push forward sigma tilde here is absolutely continuous with respect to rho. And then the fourth one is that the dy and ey are linear and bounded. So like I said, these are kind of standard assumptions. So the first one says is a mild assumption on the measure mu satisfied in many applications where mu is the law of a random field with bounded support. The second one describes the specific holomorphy of the operator f. It's also satisfied for many parametric PDE problems. We show in another paper from 2024 that one can't learn these holomorphic operators from finite data if B is an LP only. And A3 here is a relatively weak assumption. So in view of the first assumption, we expect it to hold as long as d tilde x composed with e tilde x approximates the identity on x well enough. A4 is a standard assumption. It holds, for instance, in the case of PCA-based encoders or decoders, or, for example, deep O-nets. You can see more about this in this paper from 2024, optimal deep learning from polymorphic operators based between Banach spaces, which is what this portion of the talk is based on. Also, I wanted to make a connection to the relevance to Caron-Levé expansions in computational science and UQ. So it's common to assume the measure mu on X is the law of a random field. So you have A is A0 plus this sum Ci, Yi times phi I. For some functions, A0, phi and X, where Y are these random variables and A is an L infinity. And then the Ci's and the phi's are eigenpairs associated with mu. And under some mild assumptions, this equation is then the KL expansion of the measure mu, and Yi are typically independent, so and can either have finite or infinite support. And in this talk, we consider finite support with rescaling so that Y is in -1 to 1 to the n. This fits into our framework. So suppose that Y is drawn from rho and the measure mu is given as the push forward A sharp rho, then F, and F is the the parametric solution map, taking y to u of a of y in y. And we say that phi is a Riemann if there exists a and b between 0 and infinity, such that for all xi sequences xi and L2, we have this string of inequalities a times this sum of the squared absolute value of the coefficients xi is less than or equal to the x norm of the phi expansion, and then this is less than or equal to b times the sum of the xi squared in absolute value. And suppose that X is a Hilbert space, for example, X is L2 and phi is a Ries system, then phi has a unique biorthogonal dual Ries system psi I, and this holds for the KL expansion where the phi is an orthonormal basis. In which case we can define a mapping iota from X to L2 as iota takes A to the inner products divided by the CIs of A minus A naught with psi I's in L2. This is a bounded linear map, and then we get f of x is equal to the composition of f with iota of x, which is f of y for x equals a of y drawn from mu. We can consider other parameterizations, for example, quadratic or log transformed versions of this random field. Now let's talk about the problem setup and what results we're able to compute or implement in our experiments. So let x1 up to xm be IID drawn from mu, and consider the training data xi, yi, subset of x cross y to the m, where again yi's are f of xi's plus the noise terms ei and y, and ei are these noise terms, and let n be a class of DNNs from rdx to rdy, and define f hat as again this composition of dy with n hat with ex. Where n hat is the element of the argmin over n in the family of neural networks, 1 over m times the sum from I equals 1 to m of yi, our measurements, minus this composition of di with n and e of x at our points xi, evaluation at xi in the y norm squared. Then we're able to show in the paper from 2024 with Ben and Sebastian the existence of good DNN architectures in this result. It says let x and y be Hilbert spaces. For every m greater than or equal to 3 and delta greater than 0, there's a class of tanh DNNs, so hyperbolic tangent activation functions, with width bound m over L to the 1 plus delta and depth bound log of m over L, where L is log to the 4th power of m, such that if dx is greater than or equal to the ceiling of m over L and f is in HP that's set from before, for some p between 0 and 1, then f minus f hat is bounded up to a constant by cf delta times m over L to 1/2 minus 1 over p plus ex plus ey with high probability, providing that these encoding decoding errors on x are sufficiently small, and where ey is the encoding decoding error on y. Some key features about this result: so the width and the depth are small, sample complexity is optimal up to L, and the encoding and decoding error terms are standard. And this extends in several ways, so we can also show this in the L infinity mu Bachner norm. Other activation functions can be used, like ReLU, rectified polynomial units. And the case where x and y are Banach spaces is also covered, although this case is much more complicated and provides worse generalization bounds, order m to the 1/2 times 1/2 minus 1 over p. And the problem here is also that the family is handcrafted, the family n is handcrafted, not used in practice. Key idea is to emulate orthogonal polynomials with neural networks and then set up a compressed sensing problem for the training problem. We're also able to show that fully connected DNNs are good. So the last theorem was not necessarily fully connected. Now we're able to say informally in this result that if n is any family of fully connected tanh DNNs, then there exists infinitely many minimizers that achieve the error bounds in the previous result, and such minimizers are stable and far apart in parameter space. So this states that deep learning with fully connected DNNs and sufficient width and depth can succeed, since there are minimizers that yield the optimal bounds of the main result, and they are uncountably many in number, stable to perturbations, and many of them exploding exponentially in M, have sufficiently distinct and non-vanishing or exploding parameters. But this theorem does not imply that all minimizers are good. However, our numerical results suggest that approximate minimizers obtained through training do, at least for these experiments, achieve the rate specified in the main result. And finally, we showed that deep learning is an optimal learning procedure. So we have this space HP, which I apologize might not have been defined before now. I'm just realizing that. A union over the space is HB, where B is an LP and B is in 0, 1 to the n, or sorry, 0 infinity to the n, and B's P norm is less than or equal to 1. We have this result here that says that deep learning achieves optimal sample complexity. And informally, what we mean by that is given any M linear and potentially adaptive samples, no learning procedure can achieve an error bound that is little o of M to the 1/2 minus 1 over P uniformly over F in HP when Y is a Hilbert space. So now let's talk about our numerical experiments using the same setup. So we're going to consider learning the solution operators, taking A to U of A of 3, and not just U of A, but also other components, as you'll see, of 3 parametric PDEs and mixed variational formulation. I'm going to kind of skip over that detail. I'll tell you a little bit why we choose to use mixed variational formulation, but the problems we're going to look at are the elliptic diffusion equation. So here A is the diffusion coefficient, Navier-Stokes-Brinkman or NSB. A is the viscosity, and we're considering a low Reynolds number viscous dominant problem. The stationary Boussinesq equation, so A represents the viscosity and thermal conductivity and combines incompressible Navier-Stokes with parametric heat. And in all cases, we assume mu is the law of an affine or log transform random field. The mixed formulations offer several benefits over the standard variational formulation. One key advantage is it allows introduction of additional variables that can be of physical interest, also defines solution space as a tensor product of Hilbert and Banach spaces, and naturally accommodates different types of boundary conditions, for example, introducing Dirichlet boundary conditions directly into the formulation rather than imposing them on the search space. You can see more about this in the book, A Simple Introduction to the Mixed Finite Element Method, Theory and Applications by Gattaca from 2014. Okay, so the problem here is we have our training data drawn from mu and our noisy measurements yi. We want to approximate f. So we're going to generate the measurements yi using the mixed variational formulations, the parametric PDEs using Phoenix with input data xi. The noise EI is encompassing the discretization errors from the numerical solution, and each architecture is trained from data consisting pairs xi, yi, where M goes from 10, 20, 30, all the way up to 500. And then we calculate the average relative L2 mu Bachner norm error over all the trials using a sparse grid approach. So here we fix the number of nodes per layer, either 40 or 100, and the depth either 4 or 10, such that the ratio L over N is 0.1. We initialize the weights and biases using the standard Hay uniform initializer from Keras, setting the seed to the trial number and consider the rectified linear unit, hyperbolic tangent, and exponential linear units, activation functions in the experiments. This is what it looks like for the parametric elliptic diffusion equation. We run this in 4D and 8D. So the left is 4D, middle is 8D, and right is a typical solution produced by the DNN, just to visualize what's going on. So here we're learning the map from diffusion coefficient to the solution of the PDE, and we observe what the theory predicts is that the convergence rate isn't really deteriorating with respect to the dimension. So we get a rate that's approximately order 1 over M. Here's the parametric Navier-Stokes-Brinkman equation. Here we're plotting the velocity field. We're learning the map from the viscosity to the velocity and pressure field of the fluid. And on the left, you can see the 4-dimensional result. Again, 8 dimensions in the middle. All the different architectures are labeled here. The ELU, ReLU, and hyperbolic tangent of different depths and widths. And largely, we're observing the same convergence rate, even though the dimension is doubled now. The right is the velocity. Here we change to the pressure. And this is, again, The pressure on the left is dimension 4 parametric dependence, 8 dimension in the middle, and then on the right is a typical solution produced by the DNN. And then we have a third example, parametric stationary Boussinesq equation. We're learning the map from the viscosity and thermal conductivity to the velocity, temperature, and pressure of the fluid. Again, d equals 4, d equals 8, and on the right is the velocity of the fluid. And you can see the same kind of behavior. The rate of convergence is largely observed to be order 1/m. We go to the temperature, we see the same kind of thing. On the right, again, is a typical solution produced by the DNN for the temperature. And then finally, for the pressure of the fluid, mostly agrees with the order 1/m convergence rate. Okay, so differing from prior work, we used mixed variational formulations, and this led to Banach valued operators for the NSB and Boussinesq equations. However, we observed no deterioration in the rate when y is a Banach space, in contrast with the theory suggesting this is an artifact of the proof. And the theory predicts an order 1/m error. This rate closely matches the experiments, does not deteriorate when d increases, and as our theory predicts, the approximations do not suffer from the curse dimensionality. Next, I wanted to share this recent result just recently computed by my student Kunal, who ran the Navier-Stokes-Brinkman equation. We hope to get more done, but we actually, this issue with the implementation requiring these computations of norms kind of slows things down a little bit. And I'll mention this again at the end, but here we have a comparison of compressed sensing approach with primal dual restarted algorithm with zeta prime set to 10 to the minus 8 on the velocity and the pressure of the fluid. And you can see they're both plotted on the same plot on the bottom plot here. And you can compare these to the plots on the top. This is exactly the same problem. And we observe that we get a couple orders of magnitude better convergence or error in the compressed sensing approximation on this same problem versus the neural network approximations above. Okay, so let me summarize contributions here and then wrap up. So we've shown the existence of efficient algorithms for sparse approximation and parametric PDEs based on compressed sensing with rates of convergence established in both the finite and infinite dimensional settings. Constructed families of DNNs for which any approximate minimizer of the training problem satisfies a generalization bound that is explicit in the approximation, encoding, decoding, optimization, and sampling errors. These DNNs are problem agnostic and depending only on M, and completely independent on the regularity assumptions in the target operator. We also show that training problems based on any family of fully connected DNNs possess uncountably many minimizers that achieve the same generalization bounds. And we show that the generalization bound is optimal with respect to M, so no learning procedure, not necessarily deep learning based, can achieve better rates in M up to log terms. We also demonstrate the efficacy of compressed sensing and deep learning on challenging parametric PDE problems. And the latter two, of course, involve operators whose codomains are Banach spaces. Some caveats, like I mentioned, the primal dual restarted algorithm for compressed sensing requires computation of norms at each iteration. And in particular, the components, viewing the components or what we end up actually with is a big matrix, and we end up treating each row as a different component of this discretized Hilbert valued vector. And we end up having to compute norms of each of these components. And some of our PDE examples you saw, for example, Navier-Stokes-Brinkman involve computing norms in L4, for example, for which we're falling back to Phoenix to implement these, and it's not exactly a fast computation there. So we've thought about some things we can do to speed things up, for example, projecting into a lower fidelity or coarser finite element spaces, and then using those projections to compute these norms instead, where it might be quicker. But we're open to any suggestions you might have if you have any ideas. We also note that assumption A1 for the results on the neural network approximations don't hold in all cases. It's currently an open problem whether these can be extended to the case where mu is Gaussian, for example. And we also assert, our results also assert that some minimizers are good, but not all. And Of course, techniques from statistical learning theory can provide stronger bounds that hold for all minimizers, yet these typically produce slower rates of decay in M. And finally, we show worse generalization bounds when Y is a Banach space. And our numerical results suggest that this is an artifact of the proof, but whether this can be improved is an interesting open problem. And I'll end here with some references, and thank you all for attending my talk.
Great. Thanks for giving the talk. So I'll stop the recording here, and then we can take any questions if folks might have. Yes. All right.